Hello friends, I welcome you in lecture number 9 on residues. In this lecture also we will discuss one more example on Cauchy's residue theorem. So let's start with this example. We are asked to evaluate complex integral of this function over the contour C, which is given as ellipse 9x square plus y square equal to 9 taken in counterclockwise direction. Now if we observe the function in the integral, we can consider this function as a sum of two different functions. So first we consider f of z as the notation for given function, and we call first function as function g and second function as function h. So g of z is z e raised to pi z over z raised to 4 minus 16, and h of z is z times e raised to pi by z. So that integral of f of z over contour C will be equal to integral of g plus integral of h. So this is the notation for integral along simple closed contour. Now given contour is ellipse. First we observe what is given contour or given simple closed curve is ellipse given by 9x square plus y square equal to, let me check, 9x square plus y square equal to 9. So this we can rewrite as, if we divide the whole equation by 9, we have x square plus y square divided by 9 equal to 1, or this we can again rewrite as x square over 1 square plus y square over 3 square equal to 1. So using this standard form of ellipse, we can roughly sketch the equation, roughly sketch the graph of ellipse. So if we compare with x square over a square plus y square over b square equal to 1, here a equal to 1 and b equal to 3. So here a is less than b. Now b equal to 3 means we have to go up to 3 on y-axis. So if we consider this as complex plane, this is the origin, this is order pair 0 1, or we can say that I, or we can write 0 1. So this is going to be 2i and this is 3i or 0 3. Similarly here we have to go up to minus 3i. So this is minus I, minus 2i, minus 3i, and a is 1, so we have to go up to 1. Suppose this scale on x-axis is 1, so this is 1 and minus 1. So our ellipse is passing through these 4 points. Okay, we may have rough sketch of the ellipse. So it will look like this. It will pass through these 4 points. So this is the rough sketch of the given contour, which is nothing but 9x square plus y square equal to 9, or x square upon 1 square plus y square over 3 square equal to 9. This is real axis or x-axis, this is imaginary axis. 3i can be rewritten as order pair 0 3. Similarly this is order pair 0 minus 3. This is 1, or as a complex number we write is as order pair 1 0. Okay, fine. So this is the representation of given contour. Now first we find out integral of function g along this ellipse. So for that we first observe our function g, which is z e raised to pi z over z raised to 4 minus 16. So now g of z equal to z e raised to pi z over z raised to 4 minus 16. So we know that z into e raised to pi z is analytic everywhere. Similarly, z raised to 4 minus 16 is also analytic everywhere, because polynomial and exponential function are analytic everywhere. So g of z is division of two analytic functions. So g of z will fail to become analytic at all those points for which z raised to 4 minus 16 is 0. So z raised to 4 minus 16 is 0. That means we can write this as z square minus 4 times z square plus 4 equal to 0. Okay, we have rewritten z raised to 4 minus 16 as product of z square minus 4 times z square plus 4 equal to 0. So this is again rewritten as z square minus 4 can be rewritten as z minus 2 into z plus 2, and we keep this as it is, z square plus 4 equal to 0. So from this we obtain z minus 2 equal to 0, that is z equal to 2. This is z plus 2. So z plus 2 equal to 0 if z equal to minus 2, and z square plus 4 equal to 0. Now z square plus 4 equal to 0 will give us z square equal to minus 4, and we can rewrite minus 1 as I square. So this is nothing but z square equal to square of plus or minus 2i. So therefore z equal to plus or minus 2i. So we have z equal to 2, z equal to minus 2, and z equal to plus or minus 2i, which will make this z raised to 4 minus 16 0. So g of z will not be analytic at these 4 points. So therefore g of z is not analytic at z equal to 2, minus 2, 2i and minus 2i, and these are the only 4 points at which g of z is not analytic. So it is not analytic at these 4 points only. So these 4 points are isolated singularities of g of z. So g of z has isolated singularities at these 4 points, z equal to 2, minus 2, 2i and minus 2i. Now our interest is among these 4 points, which points are inside C and which points are outside C. So we know that this distance is 1. So here we will have 2, and here we will have minus 2, and 2i and minus 2i are inside the ellipse. So we have 4 isolated singularities, 2 minus 2, 2i minus 2i. Among those 4 isolated singularities, these 2 and minus 2 are outside the contour C. So we are not interested in 2 and minus 2. We are interested in these 2 isolated singularities, 2i and minus 2i, which are inside this simple closed contour. So we will find out residues at 2i and minus 2i only. So G has isolated singularities, and among which z equal to 2i minus 2i lie inside simple closed contour C, which is ellipse here. So therefore g of z is analytic everywhere inside and on C except these 2 isolated singularities. So therefore g of z is analytic everywhere inside and on C except finite number of points, which are 2 here, except z equal to 2i and z equal to minus 2i. So therefore hypothesis of Cauchy's residue theorem is satisfied. So we can apply Cauchy's residue theorem to evaluate integral of g of z along given curve C. So for that we have to decide residues of g of z at z equal to 2i and z equal to minus 2i. So now we calculate residues of g of z at these 2 points one by one. So first we calculate residue at z equal to 2i. For that first we write our function z e raised to pi z over z raised to 4 minus 16. This I can rewrite as z e raised to pi z, z raised to 2 minus 4 into z square plus 4. Now we are interested in this singularity at z equal to 2i. So for that I keep all these things as it is, and I rewrite z square plus 4 as z minus 2i times z plus 2i. Okay, if you multiply these two, you will have z square minus 2i square, that is nothing but z square minus 4i square, and because I square is minus 1, we have z square plus 4. So z square plus 4 is rewritten as product of two linear factors z minus 2i and z plus 2i. So this again can be rewritten as, we are interested at z equal to 2i, so we keep this portion, this linear factor in the denominator, and we consider all these things in the denominator. Z e raised to pi z, z square minus 4 times z plus 2i. Okay, so therefore we have rewritten our function g in this form. So therefore g of z equal to, we consider denominator as phi of z over z minus 2i, where phi of z is z e raised to pi z over z square minus 4 times z plus 2i, and this is clearly analytic at z equal to 2i. This is analytic at z equal to 2i, because we know that phi of z will not be analytic at those points at which denominator becomes 0. So denominator becomes 0 if z equal to 2 minus 2 and minus 2i. At z equal to 2i, denominator will be non-zero. So phi of z is analytic at z equal to 2 pi, and we have to check what is value of phi at z equal to 2i. So for that we put z equal to 2i. Here we have e raised to 2 pi into 2i, that I rewrite as 2 pi I, z equal to 2i, so 2i square, that is 4 into I square minus 4, and here 2i plus 2i. So I have put everywhere z equal to 2i, z equal to 2i, here e raised to pi into 2i, 2i square minus 4, 2i plus 2i. So this is 2i. We can use that formula, Euler's formula, e raised to I theta is cos theta plus I sin theta. So e raised to I into 2 pi is cos 2 pi plus I sin 2 pi. Okay, we are using the Euler's identity, e raised to I theta equal to cos theta plus I sin theta. Here theta is 2 pi, so we put theta equal to 2 pi. Here if we put I square equal to minus 1, we have minus 4 minus 4, that is minus 8, and this is 4 into I. So now we can cancel out this I with this I, 2 will cancel out, so we have 2 here, so there will be minus 16 in the denominator. Cos 2 pi is 1, sin 2 pi is 0, so this is nothing but minus 1 by 16, which is non-zero. So g of z is written as phi of z over z minus 2i, where phi of z is analytic at z equal to 2i and phi of 2i is non-zero. Therefore, g of z has a simple pole at z equal to 2i, and residue of g of z at z equal to 2i will be equal to value of function phi at z equal to 2i, which we have obtained as minus 1 by 16. So this is the first residue, which we denote by capital B1. And because here power of z minus 2i is 1, order of pole of g of z at z equal to 2i is 1. Similarly, we find out residue at z equal to minus 2i. So for that we can write g of z. Okay, if you observe here we were calculating residue at z equal to 2i. So we have written z equal to 2i in the denominator. Now we will change here. We will replace z minus 2i by z plus 2i, and we will keep z minus 2i here. So for z equal to minus 2i, we rewrite g of z. We consider z plus 2i in the denominator, and here we have z e raised to pi z square minus 4 times z minus 2i. So let me check again. We keep z e raised to pi z over z square minus 4 as it is, and we replace z plus 2i by z minus 2i and vice versa. So it is fine. Z e raised to pi z square minus 4 into z minus 2i over z plus 2i. So here our function phi is different, phi of z over z plus 2i, where phi of z is z e raised to pi z divided by z square minus 4 times z minus 2i, and this is clearly analytic at z equal to minus 2i, and phi of minus 2i equal to, we substitute z equal to minus 2i everywhere. Here e raised to minus 2 pi I minus 2i square, that is 4i square minus 4 minus 2i minus 2i. So we substitute z equal to minus 2i everywhere in this phi function. Now this we can again rewrite as minus 2i as it is. Here we have cos 2 pi minus I sin 2 pi. Okay, again we are using this Euler's identity. E raised to I theta is cos theta plus I sin theta, and e raised to minus I theta is cos theta minus I sin theta. So here we have e raised to minus 2 pi I. So we replace this by cos 2 pi minus I sin 2 pi divided by 4 into I square. I square is minus 1, so we have minus 4 minus 8. This is going to be minus 4i. So now here negative will cancel out, and here we will have only 2, and we have minus 1 by 16. In the denominator we have negative sign. Here we have cos 2 pi, which is 1 minus 0. So this is residue at z equal to minus 2i. So we have obtained residues at both the singularities which are inside the simple closed contour C. So now we can apply Cauchy's residue theorem for function g. Now by Cauchy's residue theorem, integral of g along given ellipse equal to 2 pi I times sum of residues. Residues are denoted by b1 and b2, and 2 pi I times value of b1 was minus 1 by 16 and b2 is also minus 1 by 16. So minus 1 by 16 minus 1 by 16. So this is going to be minus 2 by 16. So finally we have minus sign outside. This is 1 by 8, and finally we have minus pi I divided by 4. This 2 will cancel out and negative sign. So minus pi I by 4. This is the value of integral of g along given contour, which is ellipse. Minus pi I divided by 4. Similarly, we have to find out integral of another function which we have denoted by h of z along this ellipse. Now h of z is nothing but z times e raised to pi over z. Now first we have to decide at which points h of z is not analytic. So we know that z is analytic everywhere. Exponential function is also analytic everywhere, but because we have z in the division, we have problem at z equal to 0. This function is not defined at z equal to 0. So h of z fails to be analytic at z equal to 0. It is analytic everywhere except z equal to 0. Clearly h of z is analytic everywhere or analytic at every point except z equal to 0. So therefore z equal to 0 is isolated singularity of h of z. Now to calculate residue at z equal to 0, here it is not possible to write down h of z in this form, phi of z over z minus 0 raised to something. Okay, so we cannot apply that method to calculate residue for this function which we have applied earlier. So here we can use the Lorentz series expansion of this function to calculate residue at z equal to 0. So for that we write our function h of z, or we express h of z as a Lorentz series, and Lorentz series in powers of z, because we are interested residue at z equal to 0. Now here we have exponential function, so we can use the Taylor series of exponential function, which is e raised to z equal to 1 plus z square by 2 factorial plus z cube by 3 factorial and so on. This was the Taylor series or Maclaurin series of e raised to z. So instead of z we have pi by z, so we replace z by pi by z in this Maclaurin series. So 1 plus pi over z plus 1 by 2 factorial pi square over z square plus 1 by 3 factorial pi cube over z cube and so on. So this is valid if z is non-zero, so we consider 0 less than mod z less than infinity, because this function e raised to pi by z is analytic everywhere except z equal to 0. Now this is the Lorentz series expansion of e raised to pi by z. So now we multiply this series by z. So we have z plus pi by z into z. So z will cancel out, plus 1 by 2 factorial, that is 2 pi square divided by 2 into z. Okay, here 1 z will cancel out. Similarly pi cube divided by 3 factorial means 6 and z square and so on. So this is the Lorentz series expansion of h of z, which is valid in the domain 0 less than mod z less than infinite. Now residue means coefficient of 1 by z in the Lorentz series expansion of function h of z. So here coefficient of 1 by z is pi square by 2. We can observe here pi square by 2 is the coefficient of 1 by z. So therefore residue of h of z at z equal to 0 is nothing but pi square divided by 2, which is coefficient of 1 by z. So therefore we have obtained the residue of h of z at z equal to 0, and z equal to 0 is the only isolated singularity of h of z. Otherwise h of z is analytic everywhere, and this z equal to 0 is inside ellipse which lies inside given contour, which is ellipse. So this is the only residue which is for given function h of z. So we have only one isolated singular point of h of z which is inside this ellipse. Okay, if you observe, h of z has only one isolated singular point which is 0, and it is inside simple closed contour C. So now we can apply Cauchy's residue theorem for h of z. H of z is analytic everywhere inside the simple closed contour C except only one point z equal to 0, which is inside C. So now we apply Cauchy's residue theorem for function h. By Cauchy's residue theorem, integral of h of z over given ellipse equal to 2 pi I times sum of residues. There is only one residue here, 2 pi I. Value of b1 is pi square by 2. So 2 will cancel out. Pi into pi square is pi cube into I. So therefore integral of h of z over ellipse is nothing but pi cube times I. So we have obtained integrals of g of z and h of z, and given function was f of z. So integral of f of z is nothing but integral of g of z over c plus integral of h of z over c. So this is pi cube into I we just obtained, and we find out what is, okay, this is integral of g, so it is minus pi I divided by 4. So minus pi I divided by 4. Okay, so if we wish we can take LCM or we keep this as it is. So this is the integral of given function which was z e raised to pi z over z raised to 4 minus 16 plus z e raised to pi by z along the ellipse 9x square plus y square equal to 9. So here in this problem, what is new thing is we calculated residues of this function which we denoted by g using this result, that we are able to express our function in this form, phi of z over z minus z0 raised to m. But for function h we are not able to use this result. So we have obtained Lorentz series of h function at z equal to 0, and using the coefficient of 1 by z we obtain the residue of function h at z equal to 0, and then integral of this function equal to integral of this function plus integral of this function, and this is our answer of given integral. Okay, so in this way we have to be careful. Every time it is not possible to apply the same result for every function, so we have to use another criteria to calculate residue, as we have done in this case. For this function we are using Lorentz series to calculate residue. So this is all about today's lecture. I hope you like it. Thank you very much.